want us to begin. We'll be looking at RSA. We had looked at it before. So for the sake of those who are not with us, we want to revisit, look at the mathematics behind RSA algorithm. I begin with the just definition of terms that we're supposed to know before we go to the algorithm. You see, RSA, what is happening is, if I wanted to send you a message, or I want to communicate with you, what I do, the message that I have, my original message, is what we call the plain text. So I want to send you that the message, but I don't send you the plain text. What I do, I encrypt the plain text. I write in a format that any intruder cannot understand it. So what I send you is a ciphertext, or we can call it an encryption. So that once you get this ciphertext, you can retrieve the message, my original message, by a process we call decryption. But now the process that I used to come up with the ciphertext is what we call encryption. Encryption, that is a process that I used. You see, I had my original text. Supposing I want to send you the word, let us meet at Afia Center, and I don't want anybody else to know that I'm inviting you to meet me at the Afia Center. I encrypt it. I encrypt that message. So what I send you is the ciphertext. When you encrypt the plain text, what you get is a ciphertext. That's what you send. And then the recipient of that ciphertext and then decrypts. That's decryption. Now, to come up with the ciphertext, I have to use an encryption key. I have to use an encryption key. Then when I send you the ciphertext, you'll decrypt it using the decryption key. So what we'll be doing, therefore, is we'll be coming up with this encryption key and the decryption key. So we in the process of this class, we'll try to encrypt plain text and then decrypt it. Is that okay? So that means in this class, we'll try to see how to come up with the keys, the encryption key and then the decryption key. Now, so we have what we call the public key. So what is it, the public key? I wanted to send you a message. So if I want to send a message, the person who is supposed to receive the message, the recipient of the message, comes up with what we call a public key. Then it publishes it. You can publish it over media, any channel. Is that okay? You make it public. That public key is just that one that can be used by anybody else wanting to communicate with you. So if I wanted to communicate with you, I'll use your public key. If Wanjiru wanted to communicate with you, she'll also use that public key. So you just prepare one public key, make it public for anybody that wants to communicate with you. So normally, after you prepare that public key, you make it public. So anybody else can see it. Anybody wanting to communicate with you can communicate with you using that public key. Now, as you prepare the public key, you also prepare, the recipient of the message also prepares the decryption key. That is the secret key. Is that okay? That one, you don't make it public. It's a private key. So we have two keys here. We have the public key and we have the private key. Both of them are prepared by the recipient of the message, the person who wants to receive the message. Is that okay? Both those keys. Now, the person who sends you a message does not prepare any key. That one just uses your public key, encrypts the message, and then sends the message to you. Then you decrypt that message using your private key. So the private key is the one that will be used in decrypting the message. So the person, supposing it was me to send you the message, supposing it's me who wants to send you the message, the only key I know is the public key, and it's you prepared it. And that public key, once you prepare it, it's inverse. You get its inverse. Its inverse will be the decrypting key that you remain with as a private key. Now, so let's go to the algorithm. The algorithm is here. So again, I want to assume that it's me who wants to send you a message. Is that okay? That is the assumption. I want to assume that it's me who wants to send a message, and the message I want to send you is X. So this is my plain text. This is my original text. Is that okay? It could be, let us meet at Lafayette Center, or let's meet on Saturday. Is that okay? So this X stands for N of those, but it's the message I want to deliver to you. Now, so since it's you who wants to receive that message, or I assumed it was you who wants to send the message to your friend. It's okay. Let's say it's you. You want to send a message X to your friend. So that friend of yours has a duty. One, to choose two prime numbers, P and Q. Is that okay? These two prime numbers your friend keeps them private. Is that okay? He keeps them private. Nobody else should know them. After choosing these two prime numbers, and they should not be equal. The two prime numbers should not be equal. After choosing those two prime numbers, your friend has another duty to get their product. And their product, we call it M. So we'll be talking of mod M. Is that okay? So your friend has that duty again. The first duty he had was to choose two prime numbers. Then after choosing these two prime numbers, he gets the product of those two prime numbers. Now, this product, M, will be a public key. Is one of the public keys. One of the public keys. Is that okay? But P and Q are private. Is not supposed to expose. He only gets the product and exposes the product to whoever wants to send a message to you. Now that was the second duty that he was to do. The first duty your friend was to do was to choose two prime numbers. After choosing two prime numbers, gets the product of those two prime numbers. It does not stop there. It gets the phi of M. Euler phi of M. Since these two are prime numbers and there are only two, the Euler phi of M is given by P minus 1 multiplied by Q minus 1. And again, this Euler phi of M, your friend is supposed to keep it secret. Don't expose it, because when you expose it, anybody can use it now to get your private key. But what is the use of this Euler phi? We shall see the use of this Euler phi. It has several uses. Now, what has your friend done? Your friend, the one who's supposed to send you a message, the one you're supposed to send a message to, has picked the two prime numbers, has calculated the product of the two prime numbers, has also calculated what? Euler phi of m. Is that okay? Now, he chooses a number relatively prime to Euler phi of m. He chooses a number, just choose that one. He doesn't calculate, just chooses a number that is relatively prime. Is that okay? So that number, we shall call it E. Shall call it E. Is that okay? So your friend had several things to do. First, he chose two prime numbers. Just chose two prime numbers. And when you are doing this, they should be large, relative. They should be large prime numbers for the security of RSA. They should be very large prime numbers. Is that okay? They should not be smaller. They should not be small prime numbers. So your friend chooses those prime numbers. Your friend calculates M, the product of the two prime numbers. He then calculates Euler phi of M. After calculating Euler phi of M, he chooses a number that is relatively prime to Euler phi of M. This number E shall be a public key. The first public key was M. The first public number, the first public key that was the first key that was made public was M. M was made public. E will be made public. Is that okay? This E, he has just chosen a number relatively prime to Euler phi of M. Now, so your friend makes those two public. What is he making public? He's making M and E public. He's making M and E public. So we can call this public key. In fact, this is, let me call it not public, let me call it the encryption key. This is the encryption key. Now, since he has made these two public, if you wanted to send him any message, you can now send. You can use these two to encrypt the message. Encrypt the message and then send the message to him. Is that okay? So shall we see how to encrypt the message? But he still has one role. But that one role, he can even do it after you send him the message. Because the role he has is just to calculate D, which is going to use to decrypt. Is that okay? This D, he can calculate it even after you send him the message. But let's just see how to calculate D. D is the inverse of E. D is the inverse of E. Mod, and this is very important here, mod phi of M. And that's why I said the phi of M should be kept private also. Is that okay? Because if you can get to know what phi of M is, and since E is public, you can always calculate D. Is that okay? Yes. So it should also be kept private. So this is the only role your friend is left with, to calculate D. And the D is the inverse of E, mod phi of M. So he's calculating this inverse using any of the methods he knows. Can use the extended Euclidean algorithm, can use the Euler phi, the Euler theorem, and so on. So he has various methods to do that. So what is the decrypting key? Decrypting key is MD. MD is the decrypting key. MD. You see, M is public, but D is private. Is that okay? But now MD, that is now the key that will be used to decrypt. I want to show you how to encrypt that message. You had X, your message was X, your plain text. The only role you have is to encrypt this message. Every other role was done by the recipient of the message. It's the recipient of the message who chose the prime numbers. Then after choosing the prime numbers, he got the product of those two prime numbers. Then he also got Euler phi of M, is that okay? Then he has calculated D, the decrypting key. But your only role is to encrypt the message. How do you encrypt? You have the encrypting key, ME, and you have your message X. See, ME is public. So you take your X and raise it to E, mod M. This is the encrypted message. You can call it Y. That is the encrypted message. Just took the message you had, the original message you had, and raised it to E. Is that okay? Mod M. This is X raised to E mod M. X raised to E mod M. So this, you get your encrypted message, which we call the ciphertext. The ciphertext, is that okay? So Y is the ciphertext. Send Y to your friend. Your friend receives Y and wants to decrypt it so as to get the plain text out of it. So what your friend does, when he receives your ciphertext Y, he raises this to D. D was secret key. Then mod M. This retrieves X. This is how it retrieves X out of that. That's how it retrieves X out of it, of the ciphertext. Yes, yes. Which you also call decrypting key. So he's the only one who knows it. He's the only one who knows it, the recipient of the message. And we are saying that the assumption is that the adversaries who can get to know M and they can get to know E, the assumption is that they cannot factor M to its prime factors. That is the assumption. Assumption is that this M is very huge, such that anybody cannot factor it to the prime numbers. Is that okay? Yeah, if you want your protocol to be secure, you're using large prime numbers. And I showed you last time on the lesson I was showing you that if you have a very small number, you can easily factor it into its prime factors. Is that okay? You can easily factor it. But if you have a very huge number, it's hard to factor it. Anybody attempting to try and factor it take ages, even with the fastest computer to try and factor that number back to P and Q. So P and Q should be chosen large enough, so that it's impossible for anybody to factor M back to P and Q, because M is public. M is public. Now, so this is how you encrypt. This is how you encrypt. So the encryption key is here. You take your cipher, plain text, and raise it to E. Raise it to E, mod M. Get the ciphertext Y. This is what you send to your friend. Is that okay? There's a condition that I've put here, that the plain text you're sending should not be larger than M minus 1. Should not be larger than M minus 1. That means, supposing your P was 2 and your M was 5. No, your Q was 5 and this one. So that means your M is 10. Product of the two prime numbers is 10. So what you're saying, therefore, is that X should not be larger than 9. We're not saying that you should not send messages which are larger. What we are saying is, if your message happens to be larger than M, you break it into blocks. Is that okay? If it happens to be larger than M minus 1, you break it into blocks, and each of those blocks is, you encrypt them separately. Encrypt this block separately. And then send the encrypted, those ciphertexts that you get. You see, supposing you split it into 3 blocks, so you come up with 3 ciphertexts. You send them as 3. Yeah? Yes. Yes. So you break them into 3, those 3, and then you encrypt those 3 separately. Is that okay? Then you send to your friend those 3 blocks. Your friend will also decrypt them separately. Then you join the messages together to form meaning.
The reason why we're doing the modular, say 2 modular 5, right? Is when you're decrypting, you know that the decryption key for cryptanalysis now will be between 1 and 4. Obviously, 5 it does not count. And then it's also to keep in mind that the product that you've been given N, given a product of P and Q, where 1 is the RSA algorithm, converts the whole, whatever your input, it converts your whole input into a product that is undecipherable. That is why you have the hashing figure 0x7, whatever. So that's the point. So 1, the product of N, which is equal to P times Q, where P is an algorithm, an RSA, depending on whatever programming language you're using. And then also the inverse of the same is hard, because if you're saying 2 modular 5 is what you're using to, where 5 is the remainder, the one that you're using to create a cipher, that means that you're using the 256 hashing bit or algorithm times that 4, or times that 3, times that 2, all the way to 1, because you're saying it's 1 to 5. Okay, M minus 1, so up to 4. Yeah.
So like so it's like between 1 5 and 4 modules.
Yeah. Each has a 256 hashing bits. Yeah. Yeah, like let me show you something. It's
kind of like a clock.
Yeah. And it's random. The product N equals to P times Q, where P is an algorithm. We have the RSA and we have the SHA, and they're both 256 bits, right? So the product N is 256 bits of a modular, depending on the input that you have, times q. This q is the remainder. What we have to yeah, that's the whole point. That's the whole.
Okay, let me take you through examples why we now want to make those keys. Now, let's say that I want to send Mugasia a ciphertext. Suppose, so if I want to send Mugasia a ciphertext, we're supposed to come up with a public key. It's the Mugasia, is that okay? The one who wants to receive, the one I'm sending the message to. And in fact, it's Mugasia again who will come up with a private key. Is that okay? My role will just be to encrypt the message I have. And I'll be waiting for her public key. I go look at where her public key is because she made it public. So I check where it is, whether it's on her website or whether it's in whichever social media. I go there, I check for the public key. I have my message. So my message, which I have, the only thing I do to it is to encrypt it. And let's see what Mugasia has to do to come up with the public and the private keys. Is that okay? And then we shall see what I'll do to encrypt my message. And then we shall also see how she will decrypt it. Is that okay? Let's suppose that she chooses P to be 11 and Q to be 17. So that is her choice. She has chosen this, and these are two prime numbers. They must be prime. Once she chooses these two prime numbers, we said her first duty is to get the product. The product is 187. Is that okay? This 187 will be a public, will be made public. Is that okay? Now, the other duty we said is for her to get phi of m. But since these two are prime numbers, we say it's easier. Just take p minus 1 times q minus 1. This one is 10, and this one is 16. That gives us 160. Is that okay? You have seen what she has done? She chose two prime numbers, did the product, computed the product, then computed Euler phi of 187. The other thing she has to do is now choose a number which is relatively prime to 160. I'll again remind you the use of the word relatively prime. When we say that a number relatively prime to 160, we mean a number which together with 160 have only one as a common factor. Is that okay? The only common factor between this number E and 160 is 1. So let's assume she chooses 7, E to be 7. What it follows is that she's supposed to calculate D, the inverse of 7, mod phi of m. This time we're using phi of m. But when we are encrypting and decrypting, we're using mod m. Yes? Yes. So what I'm saying is, you choose a number E. That number E must be relatively prime to phi of m. In our case, phi of M is 160. So I'm saying that E and 160 should have 1 as the only common factor. Number 1 should be the only common factor. They should not have other common factors. For instance, you can see she has chosen 7. 7 and 160, the only common factor is 1. She could not have chosen 8. She could not have chosen 8 because 8 and 160 have other common factors like 2 is a common factor. Is that okay? 4 is a common factor. 8 is a common factor, and so on. So 8 cannot be chosen. Is that okay? Yes. So she has to choose a number that is relatively prime to the phi of M. After choosing that number, which is relatively prime to phi of M, she proceeds and finds the inverse of that number. Is that okay? This inverse, we said she'll use it to decrypt the message. We'll send to her the ciphertext. She'll use this inverse to, yes? She'll use to decrypt. She'll use this inverse to decrypt the ciphertext. Yes. Yeah, because you see, if you are to send her a message, you are sending her a ciphertext. Is that okay? That ciphertext, for her to get the original message out of it, she has to decrypt. She is using D.
If you remember what I was showing you that we had 2 modular 5, the answer would be from 4, 3, 2, 1. The one who's decrypting it should notice, I think we covered this in one of the classes, you'll notice that the decryption key will have either, it will remain like a constant. It will always have either 5 or 4 or 3, depending on what is relative congruence is the same. The reason why we have that is because of the structure, the public and private exponents. They are based off of a prime factor. Like they're based off of, like when you're factorizing, you'll find there's a key. Each of them has. So what happens in encrypting happens in decrypting, because there's no way you're going to have 4, 3, 2, 1 encrypting and you have 7, 9 with 1 in decrypting. It has to be within the same key so that they're communicating. And then remember, it's binary. It's a binary language. Like there's no trust. I don't know who's to come to. So I have to follow the numbers. And that is what forms the mapping structures of either RSA or SHA. In the original message. Now the inverse is going to have either the modular inference or it has to have the modular inference so that it can decrypt, because it's basically an answer of the question. Like
because it solves the problem of like investing.
Yeah.
If like
Yeah. Hatujajui nani nani. Basi kama
yote in form of a number.
Yeah.
I'm the only one who has that number.
Yeah. You have a component of the answer. I have a component, because also I can't have what you have copy, because I can also use it. I can backtrack it to enter your stuff. Yeah.
Like you pay like kila mtu log.
Yeah.
Then like
Kama kitu navyo kwa mlango sahi, the only person who can enter the site ameapprove. Ametupatia fingerprint na approve. If he had not approved, we have the fingerprint, but we did not have his approval. Same thing. So when I'm decrypting, I need to have a part of the copy of the key so that it shows that we had a similar transaction before, we had an agreement before, so that I can be able to decrypt.
so like it's concept of
That's the one. Yeah. Yeah.
So if the message is the public address.
The file is the modular inference, the one in the decryption. Yeah.
Okay. Now, so she chose these 2 prime numbers. After that, got the product, which is 187. After that, got phi, you'll have phi of 187. And then she just chose a number that's relatively prime. A number that's relatively prime to Euler phi of m. Is that okay? After choosing this number, she gets the inverse of this number, mod phi of m, Euler phi of m. Not mod m, mod Euler phi of m. Now this inverse, I said, she could use the Euler theorem or the extended Euclid's algorithm. She could use any method that we've learned. We've learned the extended, which the one I've written here, extended Euclid's algorithm, or she can use the Euler theorem. Euler's theorem. To get the inverse of E. To get the inverse of E. So she must get the inverse of E, because that inverse is what she should be using to decrypt message. Is that okay? Now I'm trying to go slow so that we are together. Is that okay? I'll repeat the steps. I said I wanted to send a message to Mugasi. What she does, she has to choose two prime numbers. She will keep those two prime numbers private. Is that okay? But then she has to use those two prime numbers. One, calculate M, or N in this case, N, the product of those two prime numbers. Two, she will use those two prime numbers to get Euler phi of N. Is that okay? After getting Euler phi of N, she'll have to choose a number relatively prime to Euler phi of N. She'll have to, that one she just chooses. Is that okay? A number relatively, and I've said in this case, she has chosen 7. She has to proceed and get the inverse of 7. Mod Euler phi of N. Using whichever method. In this example, I've used the extended Euclid's algorithm. So she's getting the inverse of 7. Using the extended Euclid's algorithm, you're asking yourself, how many times does 7 go into 160? 7 goes out 2 times, and the remainder is 6. So how many times does 6 go into 7? 6 goes there once, and the remainder is 1. So this one is the GCD, just as we were doing last time. This one is the GCD. You make it, you solve for it. You solve for the GCD. So the GCD is 1 in this case. You solve for 1 from this equation going up. Solve for 1 from this equation going up. So you make 1 the subject here. Make 1 the subject of the formula. And 1 is equivalent to, when you take this on the other side, the equal sign, 1 is equal to 7 minus 6 multiplied by 1. So you substituted this here. This was the remainder. So you substituted for that remainder. The next thing you do is substitute for this other remainder as you go up. So this other remainder is 6. 6 is the same as 160 minus that. When this one goes to the other side of the equal sign. So we substitute this 6. So what we have therefore is 7 minus, instead of 6, we write the equivalent of 6 from this equation, which is 160 minus 7 multiplied by 22. Then remember this one. Remember this one outside this bracket. Now you open this bracket. When you open the bracket here, what you get is 7. 7 is 7. Then there's negative here. Expand it inside the bracket. You have negative 160 multiplied by 1. 160 multiplied by 1. Then you have positive 7 multiplied by 22. Collect like terms. When you collect like terms, this 7 is multiplied by 1 here, and this 7 is multiplied by 22. So when you factor 7 out, you would have 22 plus 1, which means 7 multiplied by 23. So what do you then come up with is this. 160 multiplied by negative 1 plus 7 multiplied by 23. So that therefore means that the inverse of 7 is 23. Because it's 23 that we are saying has been multiplied by 7 to give us 1. The inverse of a number is that which when you multiply by that number, you get 1. That means the inverse of 7 is 23 in this case. Now, so that is our D. That is what she will use to decrypt once we send her the ciphertext. That is the decryption key. That is, she keeps it, 23. The inverse of 7. The inverse of 7 is 23. So our D therefore is 23. It's the same thing. We are doing it mod 160. So when you are calculating, you just use 23. But remember, it's mod 160. Now, so what is our encryption key? Encryption key is what was made public. Is that okay? What was made public, the first thing was 187, and the second thing that was made public was E, which is 7. So that means our encryption key is this. And the decryption key is this. That is our M. Now, so let's now go and encrypt the message. You see, the whole thing has been done by the recipient of the message. So the recipient of the message has made the encryption key public, and the decryption key, the 23 part here, is private. Is that okay? So nobody knows it. And let's now suppose that we want to send her a message 91. 91 is the message you want to send to her. Is that okay? So what we have to do, therefore, is to go to the public place that she had publicized the key. We retrieve the E and the M. Is that okay? Then come, because this is our message that we want to send to her, take this 91, raise it to E mod M. M is public and E is public. Yes? Yes. What was our E? Our E was 7. So that means the ciphertext, this is the ciphertext. This is the ciphertext. 91 raised to 7 mod 187. So the only thing you need to do is to find out what is 91 raised to 7 mod 187. So I'm using the fast powering algorithm. I use the fast powering algorithm to do that. And the fast powering algorithm, 91 raised to 1 will be 91. 91 raised to 2 will be 53. And 1, you know how again? You're still new, is that okay? This guy, you're still new. Okay, so this one, fast powering algorithm, we just we just getting successive squares. The first thing we do, we are doing this mod 187. So just take 91 and raise to 1, 91. You have your calculator there, is that okay? Just get from your phone, your calculator. Oh, it's okay. Square this. You see, for us to get this line, when you square the left side, when you square the left side, you have 91 raised to 2. You square the right side, just square the right side. That's 91, is that okay? 91 times 91. We are doing it mod 187. Mod 187 means you and write the remainder. Divide by 187 and tell us what the remainder is. That was 91 square, is that okay? Then you divide by 187. And then you note the remainder, is that okay? Six, 0, 4, 6.
you get 53. So we only focus on the remainder. So we are writing.
Has he understood? So you understand what we are doing, is that okay?
Yeah.
We are noting the remainder at every stage after dividing by the mod, is that okay? The divisor, which is 187. Now, so that's the same thing we do. So you've done and found 82, 53. Now, to get the next line, again, this line, you're seeing what I'm pointing at. To get this, again, you're squaring this upper one. So when you square the left side, you have 91 raised to 4. So again, you square this. And then when you square that, the answer you get divided by 187, what you write here is the remainder. Is that okay? So what do you get when you square? 53 times 53. No, you don't square it to 4. This part, yeah, you just square, you just square in the left side and square the right hand side. What is above? Is that okay? So let me just show you again. So when you have the left side that we have here is 91 raised to 1. When you square it, you get 91 raised to 2. Just leave it as 91 raised to 2. And this one also square it. When you square it, you have 82 what? 82? 82, 81. Divide this by our divisor. When you divide by the divisor, you write the remainder. The remainder should be 53. Now to move from this step to the next step, this one is squared, gives you 91 raised to 4. Now square this one and see what you get. Just square that. 53 times 53, that gives you 2809. Divide this by our divisor, which is 187. How many times does it go there? 15 times. What is 15 times 187? 2805. What is the remainder here? That's what we note here. Is that okay? We note the remainder. That's what we write there. Now, so we cannot square the next time. We cannot square again because when you square this part, you get 91 raised to 8, which is above what we want. What we want is 91 raised to 7. Is that okay? So you cannot continue squaring. You square up to, this is the maximum you can square. Now, from what we have, we can now get to know what 91 raised to 7 is. 91 raised to 7, therefore, 91 raised to 7, 91 raised to 7, using the laws of indices, from what we have here, the same as 91 raised to 4 plus 2 plus 1. Because 4 plus 2 plus 1 gives us 7. Is that okay? 4 plus 2 plus 1 gives us 7. Using the law of indices, it says, in this case, this will be the same as 91 raised to 4 times 91 raised to 2 times 91 raised to 1, which is this step. But 91 raised to 4 is 4. 91 raised to 2 is 53. And 91 raised to 1 is 91. Now, using a calculator, what is 4 times 53 times 91? Yes?
90.
What did you multiply? 4? Yes, and what do you get? 90? 292. We are doing this mod 187. What it means, you divide this by 187. How many times does it go there? 100 and? What is 103 times 187? 19, 261, subtract. What is the remainder? That one is the remainder. That's what I wrote there. Now, so what are we doing? We're encrypting this message. We're encrypting the message to get the ciphertext. We are saying that to get the ciphertext, take your original message, raise it to E. Is that okay? Raise it to E. So that one is the ciphertext that we sent to Mugasi. She is supposed to decrypt it. She remained with the D. It's only her that knows what D is. She had calculated D and found 23. So what she'll do is take that 1 raised to 23 mod 187. That's what she'll do to get our original message. What was our original message? It was 91. Yes. She's supposed to get that 91. Yes. And that is what we want to do. That's what we are going to do. And you can. So that is how you encrypt the message, and that is how it's decrypted. So the only thing we need to do again is to show our friend how to do that fast powering algorithm down there, so that we retrieve 91 out of the ciphertext. So that when we come back from the short break, we're at the same level. Is that okay? So we just need to show him now that fast powering there. No, just this example. Just want to show him how we got that 1 squared giving us 26, that 1 raised to 4 giving us that, and so on. Is that okay? So again, give him a calculator. Yes. Now, so we want to get, what we want to get to achieve is that 1 raised to 23. But we know that our calculator cannot do that. Is that okay? Why we are doing this in bits is that a calculator cannot do that. Just try, take your calculator, that 1 raised to 23. What do you get? Times 10 raised to? Oh, that one can do it. Huh? Yeah, but the others that cannot do that. And now, that is why we do it in bits. We do it in bits until we arrive at this part. If this power was very huge, that calculator would not have done it. Is that okay? But since this power is small, relatively, that is why it's able to do it. Now, for us to arrive at that 1 raised to 23, we do it, we square, we do successive square, successive squaring. So we take that 1 raised to 1, that will give us that, to give us that 1. Is that okay? To get this next line, we square the 1 above. When you square the line above, you have that 1 raised to 2 on the left side, and on the right side, you are squaring 31 times 31, and you are doing this mod 187. What is that 1 times 31? 1? 961. Let's divide that by 187. 5 times. What's that product? 935. What's the difference? 26, and that is why you can see I had a 26 there. That's why you can see I had that 26. So it's 26. Is that okay? Yes, you can see how we got 26. Now, to get this next line, we square the one above. The left side, when you square this, you get that. Is that okay? Our interest is here. 26 times 26 mod 187. What is 26 times 26? 6. Divide that by 187. 3 times. It's 676, that was 187. 3 times. What's that product? 5. 61. What's the difference? 1. That's what you see I had written there. That's how I got it. So you now see what we are doing. Is that okay? To get the next one, again, we are squaring that 115. This point, we are squaring 115. Then doing it mod 187. You get 135. Remember, mod 187 means divide by 187 and write the remainder. At this point, you get 135. And then at this point, you're taking that 135 square and then mod 187. Is that okay? Which means divide by 187 and write the remainder. Is that okay? Good. Now, so after you've done all that, you notice that you cannot square again after that. Because when you square this should be the last one. Because when you square this power will go to 32. And 32 is above 23. The power you want is that 1 raised to 23. But when you square this, you get that 1 raised to 32. Is that okay? Yes. So that means you stop at this point. When you stop at that point, you then combine. You look at the ones you have and combine. Is that okay? Combine those that will give a sum of 23. You're looking for a sum of 23. So from the powers we have, check which ones will give you a sum of 23. For instance, if I have 23, this 23 can be written as that 1 raised to, instead of 23, I have 16. So what can I add to 16 to get 23? 7. Is that okay? 7 plus 16 will give me 23. But 7 is not here. 7 is not among these powers. So I choose one that is less than 7. 4. I have 20. 16 plus 4 is 20. And I needed 23. So I'm left with 3. Is that okay? Which is not among these powers. So I choose one that is less. So I have 22. Then when I add 1, I have 23. So this then means that 1 raised to 16 times that 1 raised to 4 times that 1 raised to 2 There's that 1 raised to 1. That's what you see here. But that 1 raised to 16 is 86. This other one is that 1 raised to 4 is 115. That 1 raised to 2 is 26. That 1 raised to 1 is that one. Get that product and divide by 187. Not the remainder. What do you get? Get that product, divide by 187, and not the remainder. What's the product? If it's 2, just divide by 187 and tell us the remainder. Just divide by 187 and tell us the remainder. Okay. We should get that 91. Is that okay? Okay, as we continue showing him, we can have just a short break. Is that okay? now to try questions. Let's try questions out, huh? Using what we've been doing. And us to try questions out. So like this first question, we've been given P and Q and then E. So we are hoping that somebody wants the message. The one who we are sending the message to has chosen P, has chosen Q, and has chosen E. So our duty now, want to find a D for him, for this person. Want to find out what is the D this person has. And then supposing our text, our plain text is 8. Want to encrypt this 8. And then after encrypting this 8, we will also decrypt the ciphertext. That is what we want to do. So, and these questions we are doing, it's you doing this. So each person does several questions for each one of you. Come and do one as we watch, and we can assist by using of a calculator where assistance. Who is the first to go? Come.
So we're trying, oh, we have P and Q. Okay, we have everything we need. So to begin with, step 1 is usually P times Q to get M. In this case, P is 7 and Q is 13 to get 17 times, 7 times 13 is 91. So we have M. Next step, we get the phi of M, which is equal to P minus 1 multiplied by Q minus 1, because both numbers are prime numbers. So in this case, the phi of M is equals to 7 minus 1 multiplied by 13 minus 1. So phi of M is equals to 6 times 12, which is 6 times 12 is that's 72. And then after this, we choose a number E such that, oh, we have E. Oh, so E is equals to 7. So we find the number D. How do we find D? D is the inverse of E, and it's mod phi of M. We can say congruent, right? It's congruent, nice. So this means that, we have to compute this actually. So the inverse of 7 mod, the phi of M we calculated was 72. So mod 72. So which means D times 7 is congruent to 1 mod 72. So I'm going to use extended Euclids to compute this. So 72 is equals to 7 into brackets 10 times plus 2, and then express the divisor in terms of the remainder. That's 7 equals 2, 3 times plus 1. So the GCD is 1. So we already have our last non-zero remainder here as 1. So we substitute back up. It will be 1 equals 7 minus 2, 3 times. Then we substitute 3. Can I? Yeah, okay, yeah. And then we substitute 2. So we know that 2 equals 72 minus 7 10 times. Just assume I've written 10 here, like that. So 1 equals 7 minus 3 big bracket 72 minus 7 10 times. So 1 equals 7 minus 72 3 times plus 7 30 times. So 1 equals, collect like terms, 7 31 times minus, this is 1 by the way, because minus 72 3 times. So express the GCD in the form AX plus BY. 1 equals 7 31 times plus 72 negative 3 times. So what we're looking for is the coefficient of, is it really coefficient of the inverse of E. So in this case, our E was 7. So what's the one that's 7 here is 31. So we found out our D is 31. So after this, I encrypt the message. Okay.
So we have D.
Yeah, we
This-
have
this
D
number
now.
is
D is 31. So
I hope it's clear to us to them because the steps are okay the way they are. It's correct.
So the next thing we're going to do is to encrypt the plain text. Okay. So for the encryption, we are encrypting the message X. We're encrypting the message X so that it becomes Y, right? So we want, X was 8. Our message X, the value of X is 8. So we want to change this plain text X into a ciphertext Y. So to do that, we say Y equals X power E mod M. Mod M. So our M was, what is the value of M? Oh, 72, yeah. It was 91. Yeah, 91. 5 of M was 1, that was 72. So our M is 91. So Y is congruent to, supposed to be congruent to, our X is 8. Our E was 7 mod 91. Yes, so here let's just use fast powering. Oh, no, actually we can get 8 power 7 very easily. Right? Yeah, so 8 power 7 mod 91 is 8 times. Let's
What's the calculator?
8 power 7 mod 91. So 8 power 7 and then divide by 91 and the remainder.
What have you found? 20? The remainder is 7.
So our Y here is 57. So that's the ciphertext. Now to decrypt, or as I guess as you can realize for encryption, we use X. Yeah, for encryption we use X and E. And then now to decrypt the message, we use M. To decrypt the message, we're going to use M and D. So as Wajiru had told us, you can see the M is common here. So let me erase. Yeah. So our Y is 57. So we already have Y. Oh, we already have Y as 57. So when you have the ciphertext Y and then you want to get the plain text, you use the formula. The plain text is X. So X is congruent to Y power D mod M. We know that M is M was 91. So X is congruent to our Y is 57. Our D was 23 mod M. So, mod 91. 91, that's 91. So here, we're going to have to use fast powering. I'm going to use fast powering, that is. So, 57 power 1 equals 57. Then 57 squared equals mod 91.
So that's good.
Yeah.
64.
64. And then 57 power 4 is 1. Also, the remainder is equal to 1. So 57 power 8 will be 1. 57 power 16 will be 1. Yeah. So 16 is closest to 23. So now I'm going to express 23 here in terms of the powers we have. So I know that 23, to get 23, I need 16 plus 7. So 7 is not here, so we'll go with 4 as the next one, plus 2 plus 1. Right? So I'm going to choose the numbers that correspond to these powers. So the power of 16 gives us 1, times the power of 4 gives us 1, times the power of 2 gives us 64, times the power of 1 gives us 57. And I'm going to compute all of this mod 91. So what do you get when you multiply 57 by 64? Mod 91.
Yes.
Yeah, 8. So we get X as 8, which was the plain text according to the message. So yeah, we have encrypted and decrypted.
So great. Now the next question. The next person. The next question is here. Just change the values of P, Q, and E, but the working is the same. Going next. Going next. Going next.
So we have the values P, Q, and E. We have the cipher value of X. We decrypt the ciphertext. So say P by Q equals M. 5 by 17. 5. So we find the Euler phi of M, which is P minus 1, Q minus 1, which is equals to 5 minus 1 by 17 minus 1. So Euler phi of M is 4 by 16, which is 64. So, the Euler phi.
It has been given, so yes,
Oh, 7. So inverse of 7. Oh, M is 64. Kupata hii itakuwa vipi? Nimechanganyikiwa.
If he is algorithm, I guess.
Hint hapa.
What they're saying that you solve for, suppose you have this, it's congruent to 1 mod 64. So you find D.
We get D. So after GCD, we check GCD 64 and 7. Times 9 and 1. So GCD is 1. And this is simple 1 equals 64 minus 61. Using the formula 7b is congruent to 1 mod 64. So D is 9. And we have B, we have 9.
Can you reverse?
Yes.
Yeah, when you reverse here, D is not 9. Because when you reverse what you're getting here, what you have here, this equation is the same as 1, is the same as 64 plus 7 minus 9.
So D is negative 9.
This is what?
Negative 9.
Negative 9. Which is what? As a positive number? No. So this is negative 9 mod 64.
Mod 64.
Mod 64. What is that? What is negative 9 mod 64? Just add this to that. 855.
55 or 45. Oh, 64. 55. So this is 55.
This 55. That's our decrypting.
So we decrypt.
So if I encrypt that, but that's the key we shall use to decrypt.
Oh, this is the key.
We shall use that to decrypt.
We decrypt
But now,
using
so that is
D and E.
M and D.
M and D.
M and D is the what we shall use to decrypt. And to encrypt we're using M and E.
And it's 64.
And so he has found D. We have M. So we need to encrypt the message, and the message has been given to us. The question has given us the message to encrypt. The question tells us that it's supposed to encrypt X, which is 6. So let us encrypt it.
So we have to find Y. X mod A, X bar A mod M. So X 6. E was 7.
Is what?
7.
7.
7. M.
Hmm? M. What was M?
62.
M is 62.
Yeah.
M was what? M is here.
Oh, M is 85. So 85. So to get 6.7.
Yeah. Those are small numbers, just multiply straight away and divide by the 5 and not the remainder.
Six for 7 would 85 in account.
That one.
What?
What is 6? What is 6 raised to 7? You calculate the answer. That's in terms of this.
7. 93.
31.
So where is 31?
So that is the ciphertext.
This is the ciphertext. So for encrypting,
To decrypt now, let's decrypt it.
encrypting.
Let's now decrypt. We take the ciphertext raised to D. Okay.
So, and D. So it is
And our D was 55. And the M, which is 85. Good. That's how we do it. I think we can complete that later. We shall get the same result. Now, so because of time, I just want us to do one question where, this one question, I want my friend in the corner and you, the friend in the corner comes up with the two prime numbers, calculates the M, then calculates D, keeps D secret. Is that okay? Calculate M, is that okay? And you come up with your own prime numbers. They should be just small prime numbers, is that okay? Calculate M. Calculate the phi of M. Calculate D. Then you choose E. Make your E and M public. Is that okay? Your M and E, make them public. All of us to hear what your M and E is. Then you keep your D secret. Then, my friend, you come up with a number. Encrypt. Encrypt, is that okay? Your own number. Yes. You encrypt your own number using his public key. Is that okay? And then that the ciphertext, make it public. The ciphertext, make it public. We are imagining that you're sending the ciphertext to him, but through a very insecure channel. Everyone can see the ciphertext. So just make it public. Now, so we have the public key and the ciphertext. Then Mugasia, what Mugasia will do, Mugasia will now attack this RSA. Mugasia does not know the private key that the friend has, but she has the public key and she has your ciphertext. So how she will attack? Using the M, you'll try and factorize that M. Come up with the two prime numbers from the M that he will, which will be public. Is that okay? You remember the way I told you last time, the mini class. So you factorize that M, come up with the P and Q. Is that okay? After coming up with the P and Q, Mugase will calculate phi of M. Is that okay? After the phi of M, since E is public, Mugase is able to get D and then can also decrypt that message. That's what we are doing. Then we will end our lesson after that. So you also, the other members of the group, they also trying to do what Mugase is doing. So because we are given the ability, come up with the prime numbers, come up with them, and keep what is secret. Then you publicize what is supposed to be public. Then you have given this guy the duty for encryption. Is that okay? Then the rest are trying to attack that RSA. But then Ukase will give us, tell us. Nimeshare kwa chat, sio?
I have one job. This is my job. Okay. You can just give Run this globe like so when I get it, I must study it fast now. But when you collect the digital happening every month, why
Now, let me share the ciphertext. The ciphertext is 366. 366. So amaliza akuja ati how we got come up with So let's now proceed. Now, what is to do? One is supposed to tell us what his P was and what his Q was. Okay. Then from there, he'll explain to us how he obtained the public key. Is that okay? He'll tell us how he obtained that at one. Then after that, he has the ciphertext. He'll decrypt that ciphertext. Okay. After decrypting the ciphertext, he'll tell us what the plain text is. And it's the only you who knows the plain text is. So you'll confirm if that is the plain text. Now, after he is done, then the cracker, one is the intruder will now come in. The intruder will come in and say, from the public domain, I obtained the public key and the ciphertext. From this public key, I was able to get P and Q. Then the intruder will be showing us how she did to get P and Q. Is that okay? Then from P and Q, she gets 5 of M, another 5 of M. Then she's able to proceed and get the decryption key, which only this one has. She's able to get it from that one. Okay. So she'll again explain that, how she did that.
So I should tell the people what my PNQ are. I should tell them what my PNQ are. Two ones. So I chose two values for two primary. First one, the P was 23, then Q was 29. And then when I multiply the two numbers, P times Q, we are going to have 6, 6, 7. So this was my M, and I put it forward as one of the public keys, if you remember. And then when we want to calculate the phi of M, it's going to be 22 times 28, which is going to be 616. Okay, now we want to get the other public key, which is E, and I'm the one who's going to be choosing it. So, E should be co-prime to, okay, E should be greater than 1 and should be a co-prime to, should be less than the co-prime of 616. Okay, so I'm going to choose a number which is co-prime to 616, and I chose the number 31. Now I want to get the D because I have phi of M, and my D should be something like this is phi of M. So you have to remember. So I have E, so I'm looking for D. So I'm going to use the Euclidean algorithm to find our D here. So 31 D is equals to 1.616. Okay, now we use the Euclidean algorithm. So 616 is equals to 31. It's going to itaingia 19 times, and then our remainder is 27. And then 31 is equals to 27 once plus 4. Then 27 is equals to 4, 6 plus 3. 4 is equals to 3, 1 plus 1. And then 3 is equals to 1, 3 plus 0. Now our GCD is going to be 1. So we're going to propagate upwards while 1 is the subject of our equation. Now I'm talking about this one here. So 1 is equals to 4 minus 3, 1. Now we want to substitute the 3, this one. So it's going to be 1 is equals to 4 minus 27 minus 4, 6. Multiplied by 1. So it's going to be something like 4 minus 27, 1 plus 4, 6. And then we substitute this 4, which is here. We're going to get 1 minus 31 minus 27 into 1 multiplied by 7 minus 27, 1. And then we now open our brackets. 1 is equals to 31, 7 minus 27, 7 minus 27, 1. Okay, so everything well added up is going to be 31, 7 minus 27, 8. Now we substitute the 27 here, this value here. So it's going to be this 27. So niweke ikiwa kubwa kidogo. 131 is equals to 31, 7 minus 6, 1, 6 minus 31, 19, 8 times. So everything added up is going to be, okay, yes, let me give the final answer. So everything added up is going to be 31, 159, and then plus 616, negative 8, which is similar to our equation above here. So we're going to see our D is going to be 159. So my decryption key was 159. Then now the decrypting. So I was sent the value 366. Okay, so 366 to the power of 159 mod 667. 667, I hope. Okay, mod 667. So my answer was 14.
Yes.
14.
14.
Yes.
That was the plain text.
Yes.
Okay. Yes, how did the intruder? The intruder coming and also decrypting without the knowledge of me.
Okay, so
Yes, yes. Oh, you define.
yes.
From there to figure out the folder. Now, what she's to tell us is that when she received the public key, she was able to complete P, was able to factorize that M to get P and Q. Then using P and Q, she's able to get Euler phi of Q. Using that Euler phi of Q, she's able to get the decryption key. That's what, and she's shows all those steps.
So we know that to get M, we usually multiply P times Q. So we're going to factorize to find the value of either Q or P, and then from that you can get the value of the other one. So when you're given the value of M, you do two things. You first of all set X naught and Y naught, which are the same, or they're equal. They're equal. And then you also find the value of C for the formula Fx equals X squared plus C. So the common value of 2 as practice is, we know it's equal to Y naught, which is equals to 2. So to calculate this, we are going to use a table that gives us the values of X and Y and the GCD of the difference and M. So when the GCD is 1, we move to the next step, but when the GCD is not 1, we stop there because that will be one of the either P or Q, yeah, one of the factors. Okay, so just erase here. So For the table, we have, oh, so we have, here we have K, and we have K, and we have YK, and we have the GCD of Y minus K, and YK minus XK, and M. So let's start with the first value of K. So to calculate this, because we're using this formula, so C, you can choose any random number, of which here I have chosen 3. So our general formula will be Fx is equals to x squared plus C. So for the first value, plus 3. So for the first value, you use the one above. So for the first K, you use the value to find here, substitute here. You use x0 for the first value of x. Then for the second one, you use x1. Then for the third one, is x2, like that. So we know that x0 is 2. So when you substitute 2 into this formula, 2 squared plus 3 gives us 7. For the formula of y, we'll use y equals x squared, y squared plus 2 plus 3 squared plus 3. Yeah, like that. Yeah. So we know the value of y0 is 2. So when you compute here, you get 2 squared plus 3, which is 7. And then you square it, which gives us 49. And then you add 3, which gives us 52 here. And then you get the difference of 52 and 7, which is 45. So what is the GCD of 45 and 667? So GCD here is 45 and 667, which is GCD. It's 1. So since it's 1, we move to the next step. We have to find K2. So for this one, we use now the previous value of x now, which is the previous x, which is 7. So 7 squared is 49. 49 plus 3 is 52. And then use the formula for y, which is here. I don't know if you can see it clearly. Let me just rewrite it here. Equals y squared plus 3 squared plus 3. So here, our y squared is yk equals to, yeah. So K2. So y squared, okay, I had calculated, so let me just check my answer. 52 squared. And then you add 3 more. So 667 is our M. So when you calculate that, you get your answer as 190. 190. So the difference between 190 and 52 is 190 minus 52 gives us 138. Yeah, 138. So the GCD of 138 and 667 is the GCD. Okay, let me just use Euclid to compute the GCD. they know. Okay. Let me grab
But
here.
you're using Euclid, so
Yeah, I use Euclid to get the GCD, of which when you use Euclid, you get the GCD is 23. So 23 is not 1, therefore we stop there. Now, it means that one of our factors is 23. So we know that Q, Q times 23 equals 667. So to get Q equals 667 over 23, which gives us 29. Yeah, 29. So I have P and Q. I can calculate the phi of M. Okay.
But the question is it what she has found as P and Q? Are they your original values you had as P and Q? That original value. That's what we wanted, because from there, whatever she's doing is what you already did. Because trying to decrypt from here, she gets phi of M, then finds D.
22 minus 1, 29 minus 1, which is 22 times 28, which gives us, yeah, 616. Yes, so, yeah, now you have Y. So, okay, the formula for encrypting is X, or decrypting, sorry, X equals Y power D mod M. You already have M, you already have the encrypted message, and then you already had E from the public key, so you can easily get D, because D is the inverse of E. So you have everything to decrypt the message.
Any some question? Yes.
The math that you're doing now, the math you're doing, that's the security bit. That's the security.
Yes.
So if you have to find P and Q, you have to go all the way and bring all those numbers.
Yes. That's why I say
You have to use
the larger primes. Because if the small primes, the one we used, like the 667, 667 was, what was M? M was 667, huh? So that one is a smaller number, anybody can find 5 of them. A smaller number. The assumption is that if we had used very huge primes, you cannot find 5 of them there. But for 667, you can try to find 5 of them.
So the security of the system.
But again, look at the 667 again, it's not very easy to find 5 of them, because that 5 of them you see must factor it. There's no other way. Way to get 5 of M of any number, must factor it first. So you see, she was able to factor it into 23 and 29. But if it was if he had used big numbers, that factoring can be done, but will take a long time. That is now what makes RSA to be insecure. Because we use bigger values, that if somebody was to try and factor using this method, using the fastest computer, it will take ages to complete that factoring. So that all that time, your communication is secure. But the method of factoring, they are there. And now they are looking at the complexity. How hard is it to factor the M? And it becomes very hard to factor it if the P and Q are huge prime numbers.
So like the RSA system is based on like it's not like purely impossible, but
Yes.
like unfeasible mathematics.
Yes.
That is not quite a lot of power to get what you want.
Yes, yes. The possibility, that is the hardness, the difficulty. The difficulty of factoring M. That is the security of RSA. Yes. That difficulty of factoring M back to its factors. And that is why the other time we said the prime number should be bigger. And you're not using even numbers or odd numbers, prime numbers. Because if the even numbers, it's very easy to factor. Because we got two goes here. So, yeah, so it's once you begin,
how many prime numbers?
Infinite.
Oh, but you can understand enough for the layer two.
Yeah, prime numbers are infinite. We make some. We don't know the last prime number. The last prime number, nobody knows it. The infinite. You have another question, yes? Yes. A question?
Less million.
How far does the question is y is equals to x squared plus c. Y is equals to x squared plus c. That's the question. And the c can be the number. So she chose on 3. You can choose c to 1, you choose c to another number. Whichever number you choose, set x naught to 2 and y naught to 2. And use the formulas to get the same result. If there's no other question, I think we end there.